Let's talk about chemical kinetics. So, what is kinetics? It is a branch of chemistry that essentially deals with understanding the rate of a chemical reaction. Rate means that we are trying to understand how fast a reaction is going to go or how slow a reaction is going to go. Okay, let's take a look at this example right here. So, this is showing us two different reactions. Reaction on the top has the reactant shown in purple color, whereas the products are shown in green. Over a certain span of time, we can see that the amount of reactants, which is the purple color, is decreasing, whereas the amount of product, which is the green balls in color, is increasing, right? The bottom reaction, on the other hand, the reactants are shown in blue and the products are shown in yellow. In the same span of time, in this case, we see that the amount of reactant decrease in the amount of, or the concentration of the reactant is not that high as compared to the top one, right? So that essentially shows us that the top reaction is much faster in comparison to the bottom reaction, right? Why is it important for us to understand the kinetics of a reaction though? So let's say if we understand the kinetics of reaction, we can predict how fast a reaction can go, how slow a reaction can go, what are the factors that I can change so that my reaction can go faster in case I'm doing this in an industry, right? I want to make my product much faster. I want to optimize the conditions so that I can have most product in the least amount of money being used, right? So this will allow us to essentially determine the rate at which a reaction will occur and the factors that will contribute to creating more products in the shortest amount of time. Okay, so let's look at some of the factors that control or influence the rate of a reaction. So for a reaction to occur, what happens? Let's say these are our reactant molecules. What is supposed to essentially happen is that all these reactant molecules collide with each other. Okay, and that is what essentially produces products. Now, the reactants essentially undergo a lot of these collisions. Not all collisions will result in products. Only certain of these collisions will be useful enough or effective enough to actually produce the products. But what can we do to increase or influence the rate of this reaction? If we can influence the number of collisions, that would influence the rate at which this reaction is happening, right? So let's look at the factors that can actually influence the number of collisions. For instance, if I increase the number of molecules right here, that is going to create more collisions. That is going to increase the probability at which these molecules are going to collide with each other, right? So increasing the concentration of the reactants can increase the rate of the reaction. Next is the physical state. What that means is, let's say if one of my reactant is solid, whereas the other reactant is liquid. In comparison to another reaction where both my reactants are in liquid state, right? This physical state will actually affect how these particles will interact with each other, how will they mix with each other, and that's why they are going to influence the rate of the reaction. Next factor is temperature. So if we increase the temperature of a reaction, we know that we are increasing the energy of these molecules, right? At higher energy, these molecules are going to collide even more. They're going to move faster, which will result in more collisions, and that can result in more collisions that are effective enough to produce products, right? Increasing the rate of the reaction. Next factor is the surface area on the reaction, right? So if there is more surface area for this reaction, that will essentially help in increasing the rate of the reaction, right? For example, we can see right here, we have a steel nail, a hot steel nail in oxygen, and you can see how it's glowing up. But if the same amount of steel in the same amount of oxygen and same amount of temperature, only thing we change is we converted the steel into steel wool. So by doing that, we are increasing the surface area of one of our reactants, and that's why it's resulting in this change in the reaction rate. Next thing is the collision energy. So like I said before, these reactants are going to collide with each other multiple times, but it's not necessary that each collision will result in the reaction to proceed to form product, right? A reaction can only occur if there is enough collision energy between these molecules whenever they collide. So having enough sufficient collision energy is very necessary for a reaction to occur, which can be again increased as we increase the temperature of a reaction, right? Now let's look at how we can actually express a particular reaction rate. So the rate of the reaction, let's say we are looking at a particular reaction where we have A as our reactant is getting converted into B, which is our product. So how can you actually determine the rate of this reaction experimentally? What is happening over time? Over time, our reactant A is getting used up and our product B is being produced. So what's happening to the concentration of our reactants and the concentration of our product? Let's say if we make a plot right here, this is concentration on the y-axis and this is time on the x-axis. Over time, concentration of A is going to decrease, right? Let me put this in blue actually. Over time, concentration of A is going to decrease, whereas over time concentration of concentration of B is going to increase, right? So if we can determine the change in the concentration of A or B over time, that would tell us what is the rate of the reaction, right? So rate is usually expressed in terms of change in concentration. Change again is usually depicted by this symbol triangle called delta. Concentration is usually depicted by square brackets. Okay, so when I put A right here, that essentially means I'm talking about concentration of A, and with this delta sign in front of it, I'm talking about change in concentration of A, okay, over a certain amount of time. And what is this? Again, change in the time or the time interval, right? So rate is essentially change in concentration of A over time. But is this correct though? What's happening to concentration of A over time? We saw that concentration of A over time is decreasing, meaning if I take final concentration of A right here at this time point minus the initial concentration of A right here over this period of time, right? I take this difference. It's going to be negative. Why? Because this concentration is lower than the concentration at the beginning, right? So that means my rate is going to be negative. Rates are always positive, right? We never talk about speed of a car in negative. If a car is going in reverse at a certain speed, we don't say that the speed is negative this many miles per hour, right? It's just in reverse. Speed is still a positive term, right? So to make this difference positive, whenever there is a decrease in concentration of a reactant with respect to rate, we always put a negative sign, right? Okay. So rate of this reaction with respect to A is going to be negative, change in concentration of A over time. And it's going to be equal change in concentration of B over time as well, right? Because it's the same rate of the reaction. If you have two passengers in a car and the car is moving at 10 miles per hour, that means that one person is moving at 10 miles per hour and the second person is also moving at 10 miles per hour, right? The rate of the reaction is going to be same. Overall rate of the reaction, right? It can be different at which the speeds at which A and B are produced separately can be different, okay? Or used up or produced, and I'll explain that. That will come in the later examples and it will become more clear. But for now, remember that rate of a reaction overall is going to be 1, right? It's going to be same for all the reactants and products, okay? So let's take an actual example of a chemical reaction, okay? So let's say we are looking at this particular reaction right here where nitrogen is reacting with hydrogen gas to produce ammonia. So in this reaction, we have two reactants, nitrogen and hydrogen, and the product is ammonia. So let's say if I'm trying to determine the rate of the reaction in terms of the concentration of nitrogen, it is going to be rate equals change in concentration of nitrogen over time, but it's a reactant, so it's going to be negative right here, which makes the overall rate positive, correct? Now, if we take a look at this, and I want to write the same expression in terms of change in concentration of hydrogen, I can say change in concentration of hydrogen over time. That's also negative. But is this correct though? Can I say that these two terms are equal? Why am I saying this? Because stoichiometry tells us that each mole of nitrogen would require thrice the number of moles of hydrogen for a reaction to be completed. So if I'm using 5 moles of nitrogen in 1 minute, I will be using 3 times the amount of hydrogen in the same amount of time, right? So essentially this number and this number right here cannot be same because I'm using 3 times the amount of oxygen in the same amount of time. So in order to make these rates same, we will be using stoichiometric coefficient right here, right? So now if I'm using 5 moles of nitrogen in 1 minute, I'm using 3 times the moles, meaning 15 moles of hydrogen in the same amount of time, and I'm going to divide that by 3, which will make the rate equal to the rate of disappearance of nitrogen, right? Same thing applies for the rate with respect to ammonia. When we talk about rate with respect to ammonia, it's going to be equals, in this case it will be change in concentration of NH3 over time, and this is going to be positive because it's a product, right? And it's increasing concentration over time, but I will be dividing this number by 2 to get the same rate for all of them. Okay, now when we compare these, what kind of question you can expect? One is simple question like, can you express the rate expression in terms of all the reactants and products, which would be like this. Or I can provide you with the rate of reaction in terms of nitrogen and ask you what is the rate of reaction in terms of hydrogen, right? So that would be, if you know this expression and we know rate for one of them, we can figure out the rate for the other. So if the rate of disappearance of nitrogen is, let's say, 5 molar per second, what is the rate for disappearance of hydrogen gas? It's going to be 3 times of that, right? So if this is 5, this would be 3 times of that. So for hydrogen, it's going to be 15 molar per second, correct? All right. Let's look at another example then. So in this case, we are talking about a reaction between hydrogen and iodine. So there is hydrogen. Oh, let me. Okay. So we are talking about a reaction between hydrogen and iodine. Hydrogen is reacting with iodine to produce HI. And in this case, the rate can be expressed in terms of hydrogen as change in the concentration of hydrogen gas over time. Negative, because again it's a reactant, will be same as change in the concentration of iodine gas over time. Negative because it's same stoichiometric coefficient, whereas in terms of the product we will be seeing twice. Okay, now right here we'll be seeing twice the amount of product being produced in the same amount of time, right? So it has to be divided by 2. So essentially whatever is the stoichiometric coefficient, you divide your rate by that number. the rate of formation of that product or rate of disappearance of the reactant. Okay. All right. So here's one of the general reactions and showing you the general expression for the rate of a reaction. So for an example, if we have AA plus BB changes to CC plus DD, the small a, B, C, and D are stoichiometric coefficients for the reactants A, B, and products C and D respectively. And you can see that rate can be written out in this particular expression right here. For reactants, it's negative and it's divided by that stoichiometric coefficient. All right, let's look at one of the workout problems right here and try and pause the video and solve this problem. Okay. Okay, so the question is regarding the following equation, which is 2 hydrogen plus oxygen changes to water, right? Express the rate in terms of changes in the concentration of hydrogen, concentration of oxygen, and concentration of water. So whenever you see these square brackets, get into the habit of calling it as concentration, right? Because this will be carrying over for all the other courses that follow up in general chemistry. Okay, so in order to express the rate, we can just write down rate equals concentration, change in concentration of hydrogen over time. Again, since it's decreasing, it's a reactant, it's going to be negative, and the stoichiometric coefficient is 2, so we divide it by 2 equals change in concentration of oxygen gas over time. Again, it's a reactant, so negative, equals change in concentration of water over time. And again, this is a product, so it's going to be positive since the concentration is increasing over time, and stoichiometric coefficient is 2, so we divide it by 2. Right? Next, part B, this is part A. So part B is asking us when the concentration of oxygen is decreasing at 0.23 mole per liter per second, at what rate is the concentration of water increasing? So what the question has given us, the rate of disappearance of oxygen is 0.23 mole or molarity, mole per liter is same as molarity, molar per second. What is the rate at which water is increasing? So the question is asking us to compare these two values, right? You can just see from the stoichiometric coefficient by itself. You don't even need this expression. You can see from the stoichiometric coefficient that the rate of disappearance of oxygen, whatever is the rate of disappearance of oxygen, rate of appearance of water is going to be twice of that, right? So if this is 0.23, water is going to increase at twice the amount of rate. So 2 times 0.23 meaning 0.46 molar per second, right? And if you plug in the numbers right in this equation, that would give you the same answer. So rate of disappearance of oxygen is 0.23. Since it's already telling you this is decreasing, it's not giving you a symbol right here because it's saying that it is decreasing. But if you plug in into this expression, you're going to put it as negative 0.23, which will make this negative, which will cancel this negative out and create it into a positive 0.23. And the question is asking us to figure out, solve for this expression outside of 2, meaning 2 times of that, which is 0.46. Okay. But honestly, for a question like this, you really do not need to write out this expression. You can just tell it by looking at the stoichiometric coefficient. Okay. Same thing. If the oxygen is decreasing at 0.23 molar per second, the question could be, what is the rate at which hydrogen gas is decreasing? So we can see from this stoichiometric coefficient itself that the rate at which oxygen is decreasing, hydrogen is going to decrease at twice the amount of rate because you need twice the amount of hydrogen, right? So if oxygen is 0.23, water is going to be twice, oh sorry, hydrogen is going to be twice of that, meaning 0.46 molar per second. Here's the solution for you as well, completely written out. Now let's look at what is a rate law. Okay. Now why do we need a rate law? We already have an expression, right? An expression only tells us how the reactant rate and the product rate are related. What is a rate law? A rate law is the law that allows us to predict the rate at which a reaction is going to happen. Okay, so this is the usual expression for a rate law. For instance, if we are working with a reaction where A is reacting with B to form C and D, the rate of the reaction is going to depend on concentration of the reactants, right? So it will depend on concentration of the reactant. A raised to the power of m, concentration of B raised to the power of n, can be x, y, whatever. And since these are just related right now, we need, whenever we put an equal sign, we need a proportionality constant. In this case, we write it as small k. And remember, this is not written in caps. This has to be small k. And you'll follow that why small and why not capital in the later on topics. This k right here is called as the rate constant. Okay. Now the important thing to remember here is that this m is not equal to a. It can be, but it's not necessarily equal to a. Same thing, n is not necessarily going to be equal to b. Okay, these m and n are going to be determined experimentally. And what is m and n? M is the order of the reaction with respect to a. Okay, and n is the order of the reaction with respect to b. Okay, and what is the overall order of the reaction? Overall order of reaction is going to be m plus n. Okay, so these are just few terminologies that we want to get out of the way. So rate is essentially same thing, molar, unit of molar per second, per minute, per hour, whatever. K is the rate constant. This is essentially concentration of the reactant raised to the power m, where m is the order of the reaction with respect to A, and B is the other reactant. N is the order of the reaction with respect to B, and the overall order of this reaction is going to be M plus N. Okay. Let's pick a simpler example to essentially try and understand what do I mean by order. So if we are just picking one very straightforward reaction of A is being converted into B, right? I'm telling that the rate of this reaction is equal to rate constant K times the concentration of my reactant to the power of m, correct? Where m is my order of the reaction with respect to A, and in this case, since I only have one reactant, m is also going to be the overall order of this reaction. Okay. Now let's say if I increase the concentration of my reactant by 2 times, meaning when I double the concentration of A, my rate became doubled. What does that mean? What is m going to be equal to? So if I double the concentration of A, K is same, my rate became twice as well, right? So what does that mean? That means M is going to be equal to 1. Yes. So such reactions are called as first order reaction. Okay. Now let's pick another example. Let's say if when I double the rate of my reaction, when I double the concentration of A, the rate of my reaction became 4 times. So when let me hear this. When we double the concentration of A, so concentration of A is 2 times, the rate became 4 times. What does that mean? M is going to be 2, right? Only then When I double the concentration of A, my rate will become 4 times. That means this is a second order reaction. Okay. There could be another scenario where I double the concentration of A. So my concentration of A is 2 times now, but the rate remains the same, right? Which means that in this case, even if I'm changing the concentration of A, my rate is not changing. So the rate is not dependent on concentration of A, meaning M is equal to 0. In this case, rate is equal to K A to the power 0. Why? Because anything to the power 0 is 1. So essentially rate is equal to K. It is independent of concentration of A, and such reactions are called as zero order reaction. Okay. In your case, we are only going to focus on three different orders of reaction, which is first order reaction where M is equal to 1, or second order reaction M equals 2, or a zero order reaction where M is equal to 0. Okay. So you can see this is just essentially repeating that if the rate doubles when A doubles, the rate depends on A to the power 1 and the reaction is first order with respect to A. If the rate quadruples when A doubles, the rate depends on A to the power 2 and the reaction is second order with respect to A. If the rate does not change when A doubles, the rate does not depend on concentration of A and the reaction is zero order with respect to A. So these are just the plots for the rate of the reaction. So if this is the rate of the reaction, on the y-axis we have concentration of A. On the x-axis, a zero order reaction would look like something like this, a straight line, meaning as the concentration of A is changing, as I'm going from left to right, the rate stays constant. Therefore, it's a zero order reaction. Whereas a first order reaction would look more like a linear line. Why? Because as the concentration of A is increasing, the rate of the reaction is increasing by the same ratio. A second order reaction, on the other hand, is when the concentration of A is increasing, rate of the reaction is increasing exponentially. So therefore, it looks like this exponential curve. So a quick question could be, we can give you this curve and I'll hide out all these points and I'll ask you, can you make a plot of zero order reaction or can you label the order of the reaction for all of these? Okay. So let's look at one of the examples, a chemical reaction. So we're looking at the reaction of NO. So we have two NO reacts with hydrogen gas to produce nitrogen and water. And this is the reaction. Now the rate law for this reaction is rate equals K NO to the power 2 and hydrogen gas to the power 1. If nothing's mentioned, that essentially means it's 1, right? So let's write down this order right here. So this is our rate law. If I asked you for rate expression, that is going to be what we did before. And this is a rate law. Okay. So right here, you can see that for NO, what is the order of the reaction with respect to NO? With respect to NO, the order of reaction is 2, whereas with respect to hydrogen gas, the order of reaction is 1. And what is the overall order of the reaction? Overall order is 2 plus 1, meaning 3. Overall order is 3, right? The interesting thing I want you guys to note right here is you can see that NO, the order of reaction for NO is same as the stoichiometric coefficient right here, it's 2. But in case of hydrogen gas, the order of reaction is 1, whereas the stoichiometric coefficient is 2. Okay, so that is what is important. The stoichiometric coefficients, the stoichiometric coefficients are not necessarily going to be same as the order of the reaction with respect to that particular reactant. Okay, remember that these order of the reactions have nothing to do with the stoichiometric coefficient. These are determined by doing experiments, and we'll look at how you can actually experimentally determine them. But the important thing is these are not the same thing as the stoichiometric coefficient. Okay, remember, order is not equal to stoichiometric coefficient, and remember that because this is the most common mistake that students usually make whenever working with rate laws. Okay, then let's try out some example problems right here. We have three different problems right here. I'm only going to work on A with you guys, and you can try and work on them by yourself. Okay. So for each of the following reaction, use the given rate law to determine the reaction order with respect to each reactant. So we have to determine it with respect to each of the reactants and the overall order of the reaction. For the reaction in A, determine the factor by which rate changes if NO concentration is tripled and oxygen concentration is doubled. Okay, so let's start with question number A here. So what's given to us is that 2NO gas plus oxygen gas is changing to 2NO2. The important thing is that the rate law for this reaction is given to us. The reaction coefficients again don't matter for us. What matters is the rate law, NO squared oxygen to the power 1. Okay, so what is the order of the reaction? With respect to NO, it is 2. Order of reaction with respect to oxygen is 1. How am I getting these? I'm getting these from the exponentials. What is the overall order of the reaction? It is 2 plus 1, which is 3. Okay. Now the question is, determine the factor by which the rate changes if NO is tripled and oxygen is doubled. So what will happen to rate? Rate is K same, right? If NO is tripled. So it's 3 NO squared. And what happened to oxygen? Oxygen is doubled, so it becomes 2O2, right? So what happened? So this will change to K. This will change to 3 square is, let me erase that. Okay, there we go. So this will be equal to K square of 3, which is 9. You can take those outside the parentheses, bracket NO squared. And oxygen, I'm going to write this right here, times 2, right? So this times 2 oxygen concentration. And this becomes equals 9 times 2, 18 times still KNO oxygen, right? This is the older rate. What happened to the rate? It became 18 times. You actually don't have to solve any of this. It's easier to just do this in your head if you have this right here. Rate is 3 squared times 2, meaning 9 times 2, 18. So what happened to rate right here? Rate would be 18 times of the initial rate, right? Okay, so now you guys can work on question B and question C. The question C is a bit tricky. It's not tricky, but it's different. So let's just take a look real fast at this. H2O2 plus 3I minus plus 2H plus is changing to I3 minus and 2H2O. Rate is given to us in this form. This is our rate law, right? So what is the rate with respect to H2O2? 1. Rate with respect to I minus 1. rate with respect to H plus. We don't see an H plus in our rate law. So what would be the rate with respect to H plus? It's going to be 0, meaning the rate does not depend on concentration of H plus. What is the overall order of this reaction? 1 plus 1, so 2, right? Okay, so here are the answers for rest of them. You can keep on working on those. Okay, now the question comes to how do we actually determine the order of these reactions, right? What's important is to figure out this order, right? We can know what is the rate of the reaction if we know the order of these reaction with respect to each reactant. How can you actually determine that? So to experimentally determine that, we essentially conduct the experiment in multiple trials. And in each trial, the concentration, the initial concentration of one of these reactants is varied and the rate of the reaction is measured. Okay, so for instance, we did one reaction at a certain concentration of A, a certain concentration of B, and we determined what is the rate of the reaction. Now we changed the concentration of A and kept the concentration of B consistent, and then we determined what is the effect of the concentration of A on the rate of the reaction. Okay, so what will happen if we change the concentration of both A and B at the same time? If we're changing both and we see a change in rate of the reaction, we cannot tell or we cannot predict, is this change in rate happening because of change in concentration of A or change in concentration of B, right? That's why in experimentally, if we are trying to determine the order, we have to keep one of these variables constant and only vary the concentration of one. So let's say if I double the concentration of A and I keep the concentration of B same, and I notice that my rate is also getting doubled, I now know that M is 1, right? So that's exactly what you do experimentally. You determine the rate of the reaction by changing the concentration of one reactant at a time. Okay, so let's look at one of the experimental data right here. You can actually do these questions verbally. This could be one of the very popular questions that shows up in chemical kinetics, where this experimental data is provided, and the question is, can you determine what is the rate law? So to determine the rate law, we have to determine the rate order of the reaction with respect to each of these reactants, correct? So this is an experimental data provided. Let's try and figure out what is the rate law and what is the order of the reaction with respect to each of these reactants. So there's a series of 4 experiments. This is the initial rate for all the 4 experiments that was measured experimentally. And this is the initial concentration for A and initial concentration of B for each of these experiments. So now, as we said, we will be comparing the 2 experiments where only concentration of one was varied, whereas the concentration of the other reactant was constant. So let's say we are trying to understand what is the order of reaction with respect to. So I'm just writing it out because we're doing this for the first time, but otherwise you do not need to write it out. Okay. So we want to determine what is the order of reaction with respect to A to begin with. So if we're trying to figure out what is the order with respect to A, we have to choose experiments where concentration of B is constant, right? We can only have one variable at a time. So let's find 2 experiments where concentration of B is constant right here, experiment 1 and 2. So what happened in experiment 1 and 2? What did we do with respect to the concentration of A? We can see that in experiment number 2, we have twice the amount of concentration of A, right? So when I doubled the concentration of A from 2.5 to 5, what happened to rate? Rate became doubled as well, right? So when the change in concentration is 2 times and change in rate is 2 times, that means what is my order with respect to A? It's 1, right? Now let's try and figure out what is the order with respect to B. So now I have to pick the 2 experiments where concentration of A is constant. So for example, experiment 1 and experiment 3. Let's compare these experiments. A is constant, so I do not care about it. What is happening to concentration of B? Concentration of B is doubling again. And what happened to the rate? Rate doubled as well. So when I double the concentration of B, and my rate is doubled, that means the order of reaction with respect to B is also 1. So what is the overall order of reaction? 1 plus 1, 2. What is the rate law? Rate equals K concentration of A to the power 1, which we don't have to write, and concentration of B to the power 1, which again we don't have to write. So this is our rate law for this particular reaction based on the experimental data given to us. Great, we did this verbally, right? Very simple. Sometimes you might come across numbers that are very tricky that you cannot solve just by looking at it, cannot solve in my head. Okay, what do you do in those cases? Let's try and solve for, again, for the order of A. Okay, I'll give you one example. So we have two different experiments. First thing is same, that we want to compare experiment 1 and 2 because here concentration of B is constant. So if you want to compare 1 and 2, for comparing you essentially just take ratio. So rate for number 2 over rate for number 1. We're going to take this ratio. What is the rate expression? Rate expression is essentially rate equals K A to the power M times B to the power N, right? Over K, and this A is going to be concentration for experiment number 2, concentration for experiment number 2. Concentration of A to the power M for experiment number 1, for experiment number 1. This is essentially just the rate law, the general rate law, right? We know that K is same, so it gets cancelled. We know that in this case B is same, right? It's 3 times 10 to the power negative 2 for both the experiments, so B get cancelled. What are we left with? We are left with A2 to the power of M and A1 to the power of M. We can also write this as, since it's same power, we can just put the whole thing in parentheses, right? And we can write it as A2 over A1 to the power of M, right? Now we just plug in the values that are given to us. Rate 2 is 3.5 times 10 raised to power minus 3 divided by 1.75 times 10 raised to power minus 3 equals A2 is 5.00 times 10 raised to power minus 2 divided by 2.50 times 10 raised to power minus 2 to the power of M. If we solve this, this comes out to 2 equals 2 to the power M, correct? Now if you try and solve this, that means M is 1, right? We'll do the same thing if you want to figure out order with respect to B. And now we are going to, instead of experiment 1 and 2, we are going to choose experiment 1 and 3. Right? So if the numbers are complicated and you cannot solve it in head, you can just write it down and try and solve it in this manner. Okay. Here's the solution provided to you as well. So you can take a look how this was solved if it's difficult to do the experiment in head. Here's another workout problem, very similar pattern, very similar manner. So let's take a look at this. Feel free to pause the video if you want to do this problem by yourself, and then come back and take a look at the answer that we are going to solve right here. Okay, so now we are looking at this particular reaction. Many gaseous reactions occur in car engines and exhaust systems. One of these is NO2 plus CO changes to NO plus CO2. Rate law is not given to us. Rate equals K NO2 to the power M, CO to the power N. The generic rate law is given to us. Use the following data to determine the individual and overall reaction orders. B. Calculate K using the data from experiment number 1. So we'll worry about B later on. Let's start with A. We want to determine what is the individual order with respect to each reactant. Okay? So let's say if I want to figure out what is the order with respect to NO2, I have to choose the reaction where concentration of CO is same. So let's find two experiments where concentration of CO is same. Right here, point 1, point 1. So we'll choose experiment 1 and 2. Okay, so what is happening in experiment 1 and 2? What happened to concentration of NO2? It changed from 0.1 to 0.4, which means it became 4 times, right? So when I quadrupled the concentration of NO2, the rate changed from 0.005 to 0.08, okay, which is essentially 16 times. 5 times 16 is 80, okay? But let's try and do this in here. But if you were able to solve it just in your head, you can see when I quadruple the concentration of NO2, my rate became 16 times. That means what is M? M is going to be 2. Okay, but let's try and do this using actual expressions. So we're comparing experiment 2. So what I'm trying to solve for, order with respect to NO2, or you can say I'm trying to solve for M. Okay, when you're trying to solve for M, I'm going to look for experiment 1 and 2. So rate of 2 over rate of 1. It doesn't matter. We can have rate of 2 over 1 or rate of 1 over 2. Wouldn't make a difference. Equals K NO2 concentration to CO concentration to K NO2 concentration for reaction 1 to the power M, CO concentration for reaction 1 to the power N. Since CO is same, it gets cancelled, K gets cancelled, so I'm left with concentration of NO2 for reaction 2. The concentration of 2, oh, 2 over concentration of NO2 to the power of 1 all raised to the power of, let's make this a bit bigger for this question, all raised to the power M. Okay, so let's plug in our numbers now. So rate of 2 is 0.080 divided by 0.005 equals 0.40 divided by 0.10 all raised to the power of M. This is 16 and this right here is 4 to the power M, meaning M is 2. Yeah, awesome. Now let's look at, try and solve for N. So when we are trying to solve for N, we want to look at two different experiments where concentration of carbon monoxide is changing, but NO2 is same. So let's look for two different experiments where NO is same. I can see experiment 1 and 3. So what's happening in experiment 1 and 3? NO2 is same, but CO is changing. So when we doubled the concentration of CO from 0.1 to 0.2, what happened to rate? Did not change, right? So if the rate did not change, what would be the order of reaction with respect to CO? It's going to be 0, since it's not changing, right? So essentially rate is going to be with respect to CO. If we think of, it's not dependent on CO, right? It's not changing, so it has to be 0, meaning this is going to be 1. So it is not dependent on concentration of CO. Okay, so what is the order with respect to NO? It's NO2 is 2, or with respect to CO is 0. So what is my final rate law? It's going to be rate equals K NO2 to the power 2. I can write down CO to the power 0, but if it's anything power to the power 0, essentially it's 1. So there's no need for us to write CO right here. Okay, so this is my rate law. So what is the order with respect to NO2? It's 2. Order with respect to CO is 0. What is the overall order of the reaction? Overall order of the reaction is 2 plus 0, meaning 2. Okay? That is part A. Now going to part B. Calculate K using data from experiment 1. So this is telling you specifically that it wants you to calculate the rate constant using the experiment 1 data. But sometimes it will not be very specific which experimental data. You can choose whichever experimental data. All of them should actually give you the same rate constant because K is a constant term. Okay, so let's try and solve this right here. Let me make this smaller. Okay, so it's visible. Now let's try and solve for this part. Okay, so now we know that what is our rate of the reaction? Our rate is actually K NO2 to the power 2. So the question is asking to figure out K. Do we have the rate given to us? Yes. Do we have the concentration of NO2 given to us? Yes. Let's just plug in the numbers and get our rate constant. So based on experiment 1, my rate is 0.0050 mole per liter second equals K. Concentration of NO is 0.1, so 0.10. Let me increase this, mole per liter squared, right? So now what would be K? K will be 0.005 mole per liter second divided by 0.10 squared mole square per liter square, right? So if we try and solve for this, mole and this mole got cancelled, liter and one of these liters got cancelled. So K, oh, K equals 0 point, oh my god, let me move this up. Oh, not you. Can I move the whole screen up? Okay, there we go. So K, where is it? K, where is it writing? Equals 0.50. What's the unit? You can see this will essentially go inverse. So it will become liter. Oh my god. What am I writing? 0.50 liter. Oh, it's a mess. Okay, I raised it. Let me write it down again. K equals 0.50. So you can see from the units we have inverse second and inverse mole. So it's a liter per mole second, right? So that's our value of K. Okay, you can also find the answers in the slides right here. So let's confirm what we did is correct. Yes, with respect to NO2 it is 2. With respect to CO it is 0. So rate law is K NO2 squared. Overall rate is second order. And our answer for K is 0.5 liter per mole second. Okay. Now there's another workout problem. Let's take a look at that. Okay. So the question is asking what are the units K, which is a rate constant, for the following rate law. So if rate equals K A times B cubed, what is the unit of K? So we can solve it. So very similar to how we solve the numbers usually. So just plug in all the units for each of these. So what is the unit for rate? It's usually molar per unit of time. What's the unit of time that we see in options right here? It's seconds. So I'm just going to go with second. It's molar per second equals K. This is concentration of A, so what's going to be the unit of A? It's going to be molar times K times molar times concentration of molar, again B, so molar cubed, right? So 1 molar gets cancelled. What is the unit of K? K is going to be 1 over molar cube second, which can also be written as molar cube inverse and second inverse. So do we see an option like that here? Yes, the option is D. Is that correct? Yes, that is our correct answer. Now, why did we do this question? Why? Because sometimes a question can be very simple. I might not give you what is the rate law for a reaction. I'll give you a reaction and I'll tell you that the value of K for that particular reaction. For example, I'll give you A plus B is changing to C, and I tell you that the rate constant for this particular reaction is 3.00 times 10 raised to power 8, which is really high, molar 3 inverse second inverse. Okay, can you tell me what is the order of the reaction? How can you figure out what is the order of this reaction? We do not know what is the rate law. We do not know what is the rate order with respect to any of these reactions, right? But we can determine it just based on the units of K. So we just figure out that the unit of K in this case is very similar to the question that we did before, right? The units of K can help us figure out what is the overall order of the reaction. So what is the overall order of reaction with respect to this particular reaction? It's 3 plus 1, meaning 4. So what is the order of reaction for this particular question? Overall order is going to be 4. Okay, so what is the order of reaction? It's a fourth order kinetics, which honestly you're not going to be asked a question regarding, but with respect to kinetics and with respect to just the rate constant with respect to units, that is something that you can easily answer, right? So you can try and solve for the units of K for each order of the reaction, just how we did here, and you should be able to get the units of K as shown here. Okay, so my suggestion is go ahead and try it, and you don't have to have A and B. You can just try with rate equals K A to the power 0 for a zero order reaction, right? A to the power 1 for a first order, A to the power 2 for second order, A to the power 3 for third order, and just determine what is the unit of K, right? Okay, moving on, we see another question. So if a reaction has a rate law of rate equals A to the power 2, B to the power 2, by what factor will the rate increase if the concentration of A is doubled and the concentration of B is tripled? So rate law is given to us. We can just try and do this in our head. What will happen to the rate, right? If concentration of A is doubled, so it becomes 2 squared, meaning 4, times B is tripled, so 3 squared, meaning 9. So 4 times 9, 36. Yes, A is doubled, so if A is doubled, it becomes 2 squared, so it becomes 4 times, and when B is tripled, it becomes 3 squared, 9 times. When both of them are changing together, it's going to be 9 times 4. See if our answer is correct. That's correct. Right. There's another workout problem. It's very similar to what we did before, where experimental data is given to you. and you have to determine what is the order of reaction with respect to SO. Actually, this should be SO2. So with respect to SO2, with respect to oxygen, and what is the overall order of the reaction. Then write the rate law and determine the rate constant. So it has three parts: order, then rate law, and then the rate constant. Okay, so I'm gonna let you guys work on this. Answers are given to you. Go ahead and take a look once you are done with this question. Okay. Okay. And I'm gonna stop this right here, this particular lecture, and we'll begin with the integrated laws in the next video.